S-Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
There are certain forms of first order partial differential equation, but some are the very typical forms. They have been given some names, like if we are going to discuss one of the forms, Lagrange's form.
If you want to study this topic in detail, refer to the book by S-Chan Publishing. Link is provided in the description box.
So welcome to S-Chan Academy. I, Dr. Neelam, welcome you in this lecture. Today we are going to study this Lagrange's form of first order partial differential equation and then its solution. This is first order partial differential equation. So we will be using this abbreviation for partial differential equation and which is linear in nature. So first of all, it should be linear in nature. Linear and order we have discussed in our previous videos where we have started the partial differential equation. So there are certain forms of first order partial differential equation. So one of the forms is called Lagrange's form. Lagrange's form of first order partial differential equation. In this form, the partial differential equation should be given in this way. Capital P, small p, capital Q, small q is equals to R, where this P, Q, R, P, capital Q and R are functions of the independent variable, and the independent variable, let us say, are x and y for this case. So they are functions of x and y, and let us say the unknown function is u, so they may be functions of x, y and u. That is, these two are the independent variables and this is our unknown function. And the small p and small q, since it is the first order partial differential equation, therefore this small p is the notation for the first order partial derivative of this u with respect to x, that is the first independent variable, and this q is written as first order partial derivative of u with respect to y. So if any differential equation is given in this form, it is called as that it is given in the Lagrange's form. So there is a particular method to solve this Lagrange's form, and for that method we need to form the auxiliary equations first. So first we need to form the auxiliary equations. Now what are the auxiliary equations? So we will write the dx, that is, because dx and y are our independent variables. So independent variables dx upon this capital P, that is the coefficient of first order partial derivative of u with respect to x. So the coefficient of first order partial derivative of u with respect to x is capital P. So it should be written in the denominator of dx. Then the second independent variable is y, and the coefficient of the partial derivative of u with respect to the second independent variable, that is y, is capital Q. So therefore this q will be written here. And then the rest of this is our unknown function, and this r should be written here in the denominator of this u. So that's how these auxiliary equations will be formed. Now we must remember that the partial differential equation should be strictly in this form. If suppose it is in this form, capital P small p plus capital Q small q minus r is equal to 0. If it is so, then we need to convert it in this form, and then this because otherwise there will be a difference of a minus sign, because if we are going to write down this minus r as the denominator of this du, then that will be creating a trouble for minus sign. So first thing we should be clear is that the differential equation should be written strictly in this form only, pp plus qq is equals to r, and then we will form this auxiliary equation. So what is the working rule to solve this Lagrange's form of differential equation? So the working rule says that We will solve these set of auxiliary equations and we will get two relations. Now let us say we are getting the relations u is equals to c1 and v equals to c2. These two functions we are getting, where u and v, they can be functions of x and y. So it can be written as u xy is equals to some constant c1 and v xy equals to some constant c2. Then the general solution can be written as, a function of u and v and this equals to 0. So that's how the final solution will be written for a first order partial differential equation which is in Lagrange's form. So we will take one example to make it more clear. So the question is, find the general solution for ux minus uy plus u is equals to 0. So we should be very clear about the independent variables and the unknown functions. So here the independent variables are x and y are the independent variables. Therefore, the final solution should be written in terms of the independent variables and our u is our unknown function for which solution needs to be found out. So this is unknown function. So we will write down this strictly in form of the Lagrange's form. So ux minus uy is equals to minus u. So here capital P is 1. If we compare it with the standard Lagrange's form, capital Q is minus 1 and R is minus u. Remember, we should not take the coefficient of u, but this entire thing will be considered as our R. Therefore, we will form the auxiliary equations now. We will use this abbreviation AE for auxiliary equations. So it will be dx over 1, dy over minus 1 and du over minus u. So this is the formation of the auxiliary equation. So now this next step is that we need to find out the solution, two set of functions for out of these three relations. So let us say the first relation we are going to consider as dx over 1 and dy over minus 1. So they can be integrated clearly. So it is y is equal to minus x plus c1. So it can be written as x plus y is equals to c1. So this can be considered as one of the functions. Let us say it is some u or v, whatever we would like to give some name to this. So this is one of the relation we got for this from this auxiliary equation. Now we can take second combination as dx over 1 is equal to du over minus u. And we need to integrate that. So it comes out to be x is equals to minus of log u plus log some c2. So it comes out to be, if we write, either we can leave it as it is or we can convert this in form of this. So we'll write this as c2. So this can be written as log of u is equals to c2 minus x. So u can be written as e raised to the power c2 minus x. So u is a function of x and y. So then the final general solution can be written as f of e raised to the power c2 minus x and x plus y and this equals to 0. X plus y minus c1. So this will be the general solution. Either it can be written in this form or it can be written in form of u is equal to some function of v. So either way the general solution can be written. So this is for the solution of the partial differential equation when it is given strictly in form of the Lagrange's form. Now there are certain situations when the given differential equation is not strictly in the form of Lagrange's form, but it can be converted to that. So that is called method of multipliers. So that type of differential equation will be solved as by method of multipliers, where these auxiliary equations are not giving the clear relation between x, y. So method of multiplier set. So let us say that these are this is P, dy over Q and du over R. So these are our auxiliary equations. Now let us say L, M and N can be used as multipliers and they may be constants or functions of x, y and u. They may be functions of x and y and u. So in that case, we'll use this auxiliary equation as dx over p, dy over q, du over u, and this will be written as L dx plus n dy plus n du divided by Lp plus mq plus, so this was r, plus nr, and these L, M, N are chosen in such a way such that the denominator of this L dx plus m dy plus n du is equals to 0, such that Lp plus mq plus nr is equals to 0. Now if this will be equal to 0, this will definitely give one of the relations, and then that relation will be used to find out the solution of the given differential equation. Now the method of multiplier will be made clear by taking this example. So we'll solve this example by taking L, M, N as multipliers. So we need to solve this differential equation, which is first order differential equation, which is linear in nature. So if we compare it with the standard Lagrange's form, so this is R capital P, this is R capital Q, and this is R capital R. So we will form the auxiliary equations for this. So dx over this capital P, so it is mz minus ny, and dy over nx minus lz, and du over ly minus mx. Now here it is clear that none of the pair in this auxiliary equations can be solved to get some explicit relation. Therefore, there is a need to use the multipliers. So here we will use the multipliers as, let us say that L we are taking as x, m as y, and n as u. Let us say that we are taking these multipliers as L, M and N. So we will see that Lp plus Mq plus Nr is equals to, because they should satisfy the condition that should be equal to 0, otherwise they will be of no use for us. So x into mz minus ny plus m, instead of m we will write this y nx minus lz, and we will take this n as z, and plus z into ly minus mx. So if we solve this, this becomes mxz minus nxy plus nxy minus lyz plus lyz minus mxz. So we can see that mxz gets cancelled with this one, this gets cancelled with this one, and this gets cancelled with this one. So it comes out to be 0. Therefore, the set for L, M and N as x, y and z can be of use for us. Therefore, we will rewrite this differential equation. So this will be one set of multipliers we are going to use. Now there is need of another set of multipliers also. Now the question is that how to decide that how many multipliers are required. See, it depends on this given differential equation and the auxiliary equations made out of it. So, in this case, when we are having this as our auxiliary equations, it is clear that none of these dx by p, dy over q and du over this r, they are explicit in nature and they are not giving us one of the relations. So, if one of the relation we can obtain from this, we need only one set of multipliers, and if they are not able to get some explicit relation, we need two set of multipliers. So, in this case, we need two set of multipliers. So, we need one more set of multipliers. So, let us see that what is the another set of multipliers. So, if we, this is another set of multipliers. So, if we take L, M and N as it is as multipliers. So, let us see that LP plus MQ plus NR. So, this equals to L into Mz minus Ny, because L, M, N are involved in this denominator, therefore, we are using that L, M, N. So, L, M and M into Nx minus Lz plus N into Ly minus Nx, and let us see if it comes out to be 0 or not. So, if we simplify this, so it becomes MLZ minus LNY plus MNX minus MLZ plus NLY minus MNX. So, MNX gets cancelled with this one, NLY, MLZ. So, this comes out to be 0. Therefore, this second LMN can be taken as a set of multipliers. So, we have two set of multipliers, one is XYZ and another is LMN. So, we will be using them to get two explicit relation for this. So, now for this given Lagrange's form of differential equation where the auxiliary equations are not able to give explicit relations, we have used the method of multipliers. So, we have chosen two set of multipliers, that is one is XYZ and another is LMN. We will solve this in the second part of the video.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy. So, in the second part of the video, we will take the rest of the part. So, in the first part of the video, we have discussed about the Lagrange's form of first order linear partial differential equation, and then we have discussed the method of multipliers, and we have started one question for this method of multipliers where the method of multiplier is when the auxiliary equations, they are not able to give us an explicit relation. So, we have already taken one example. So, in the first part of the video, we have discussed this much, that we have taken one question to solve this by Lagrange's form of differential equation and by using method of multipliers. So, these were the coefficients of P, Q and this is the coefficient R. So, in this one dx, dy, du, it is clearly mentioned here that it was not able to give us the explicit relation. Therefore, we had to take this method of multipliers, and the multipliers have been chosen as x, y and z, and here the multipliers have been chosen as L, M and N. So, we will see that this auxiliary equations, so dx over the coefficient was mz minus ny is equals to dy over mx minus lz, and since the third one is z, so we need to take z here. So, ly minus mx, and since we have chosen two set of multipliers which we will be taking here, so it is x dx plus y dy plus z dz, and this is divided by 0 because we have already shown that for this x this L has been replaced with X, M has been replaced with Y, and N has been replaced with Z. Therefore, this can be written as XP plus YQ plus ZR. So we have already shown that it comes out to be 0. So we are using this here. And then the second set of multipliers has been taken as L, M and N. Therefore, LDX plus MDY plus NDZ is equals divided by 0, because it has been shown already that they are coming out to be 0. Now, since in this auxiliary equations, none of these dx, dy, dz are able to give us explicit relation. Therefore, we will be using these two to get the solution for the differential equation. So, we will take this x dx plus y dy plus z dz is equals to 0, and we can integrate it, and integration is showing that it becomes x square plus y square plus z square is equals to c1. So, one relation we obtained by the first set of method of multipliers. So, this is we have got from the first set of multipliers. Now, the second set of multipliers was L, M and N. Therefore, L dx plus M dy plus N dz is equals to 0, and if we integrate this, since L, M and N are constants in this case, therefore, the integration is going to give us Nz is equals to C2. Here. So, we obtained two set of relations. So, the general solution can be written as, there are two ways to write the general solution. Both have been used in the standard textbooks. So, either we write that f of x square plus y square plus z square minus c1 and lx plus my plus nz minus c2 is equals to 0, or the second way of writing down is either of the one can be taken on the left side and the other one will be written on the right side. So, it is, if we take the first relation on the left hand side, so it is function of the second one, Lx plus My plus Nz. So, that is how the general solution for the first order partial differential equation, which is following this Lagrange's form and where the multipliers are required to get the explicit relation. So, that is how the general solution will be written. So, now we will discuss that how to solve the nonlinear first order partial differential equation. So, nonlinear partial differential equation, it has been typically divided into 5 types. So, we will discuss all 5. So, nonlinear first order partial differential equation. So, we are using this abbreviation PDE for partial differential equation. So, there are, as I said, that there are basically 5 types. So, type 1. Type 1 is if the differential equation is given in this form, f of pq is equals to 0, where p and q, of course, they denote the first order partial derivative of the unknown function with respect to x and y respectively, if the set of independent variables are x and y. It is not necessary that the set of independent variables needs to be taken as x and y. They can be x1, x2, x3 or y1, y2, y3. So, we need to categorize our this set of independent variables and the unknown function properly. Type 2 is if the equation involves z also. So, here z is our unknown function. So, it is all the forms have been considered as the standard forms. So, in some of the books u has been taken as the unknown function, and in some of the books z has been taken as the unknown function. It is depending on the unknown function, this p and q will be written. So, if suppose like in this case, this z is our unknown function. If z is our unknown function, then this p will be written as del z over del x. And if we would have taken u as an unknown function, then p would have been written as del u over del x. So, these things should be taken care of. So, type 3 is when this left side is given in terms of px and this let me say f1, and right side is given in terms of q and y, where p is the derivative with respect to x and q is the derivative with respect to I. So this is this can be solved as the variable separable form, and this is called as the variable separable form. Variable separable form. So fourth is it is called as the Clairaut's form. Clairaut's form. So the solution for this Clairaut's form is the most easy, and we say that the differential equation is given in terms of z equals to px plus qy plus some function of pq. So here z is our unknown function, so we are maintaining that z is the unknown function throughout these types. And then fifth type is called as the Charpit's form. For Charpit's form, there is no strictness that the differential equation should be written in this form. If the given partial differential equation does not fall in these four categories, it can be solved definitely by the Charpit's form. So we will take them one by one. So in the first form, it is very easy to write down the solution for this first form. This p and q will be replaced with a and b, where a and b are the constants. So for type 1, we start with type 1. So where f p q is equals to 0. So in this one, we will assume that let z is equal to ax plus by plus function of ab is the solution for the given differential equation for given PD. So if it is so, if we derive this, if we find out the derivative of this with respect to x and y, so del z over del x will become a and del z over del y will become b. And here this is the function of a and b, and since a and b are constants, therefore this function will, let us denote it with some other function. Let us say this is f2, so that we should not get confused between this f and then this f. So then in the given differential equation, this this is nothing but our p only, and this is nothing but our q only. So p will be replaced with a and q will be replaced with b, and b can be written as a function of a because that function will be found out using the given differential equation. So we will take one example to make it more clear so that there should not be any confusion regarding that. Now on substituting this p is equal to a and q equal to b in the given differential equation, it will be giving us a relation that b is equal to phi a. Therefore, the final general solution will be written as z is equals to ax plus b will be replaced with phi a y plus f of ab. So that's how the general solution for this first type differential equation will be written. So there is not much confusion in this. Then second type was when the differential equation involves the unknown function also. Now for this unknown function z, here the unknown function is z, so we need to make this some substitution for it. So unknown function is given as z. So we will make this substitution that let us say z is equals to z of u, and where u will be found by the combination of x and x plus ay. So for this, if we will find out del z over del x, so it can be written as del z over del u into del u over del x. And since z is a function of u only, therefore this partial derivative will be replaced with the ordinary derivative. And del u by del x from this we will get, del u by del x we will get from this one, and this is 1. So this comes out to be dz over du. And similarly, we will find out del z over del y, and since using the same concept, so this is del u over del y, and from this we will get del u over del y as a. So it comes out to be a dz over du. So the given partial differential equation will be converted into an ordinary differential equation in z and u, where z will be your unknown and u will be the independent variable on which this unknown function is relying upon. Therefore, this which can be solved quite easily because we have already discussed these techniques of solving first order ordinary differential equation in the previous videos. Then the third type 3 is the variable separable form. So variable separable form, they can be easily integrated upon. So there is no set procedure for this. They can be integrated separately. So let us say that we will let f1 px is equals to a, some constant, and f2 qy is equals to some other constant. We will integrate this one, which will give us one relation, and we will integrate the second one, which will give us a second relation, and then this general form can be written. Then the fourth type. Now fourth type is the Clairaut's form. So Clairaut's form is that z is equals to px plus qy plus f of p and q. So part of this we have already discussed in the type 1. So solution for this type of differential equation will be written as z equals to ax plus phi a y plus fab. By letting that, let us say that the solution is this, z equal to ax plus by plus fab, and this will be reduced to this. So in the similar lines, like we have discussed the solution for the type 1. Then the type 5 is the Charpit's form. Now if we look at these first 4 forms, there are a set of rules which the partial differential equation must follow. For this type 5, if none of the if the given partial differential equation does not fall in any of these 4 forms, then it can be solved by this Charpit's form. So in this Charpit's form, we will form the set of auxiliary equation like we have done for the Lagrange's form. The formula will be little different, and then the auxiliary equations will be solved in the similar manner like we have done for the Lagrange's form in the previous videos. So the auxiliary equation for the Charpit's form will be written like this: dx over minus del f over del p, dy over minus del f over del q, dz over minus p del f over del p minus q del f over del q, dp over p into del f over del z plus del f over del x is equals to dq over q del f over del z del f over del y. So they are the auxiliary equations which we have formed by the given differential equation. Now this part is also there where phi is written as, and the partial derivative of this phi is written as. Now this phi is nothing but it is the relation in all x, y and z. So if any of the relation we need to find out, so this can be used for that in that case. So these out of these 5 relations, so this is 1, 2, 3, 4 and 5. We will definitely be able to get at least 2 relations out of them like we have done for the Lagrange's form, and then those 2 relations can be written in form of can be used to find out the general solution of the given differential equation. So we have discussed about the 5 forms in this part of the video of nonlinear first order partial differential equation, for which the solution can be written quite easily, but first 4 forms were having some rules are to be followed for that it should be equation should be strictly in form of a PQ or PQZ, or it should be in variable separable form or in the Clairaut's form. And if the given differential equation does not fall in any of these 4 categories, then that differential equation can always be solved using Charpit's method. So we'll conclude here. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.